And so we're ready to go. So thanks everyone in the audience for joining us for the second instance of the Updates in Cooperative AI seminar series. I'll note that the first recording is now up on YouTube. In case you missed that, you can just go to our YouTube channel and it's there in case you want to catch up. But for now, I want to move on to our speaker for today, who is Raphael Köster. So Raphael is a research scientist at Google DeepMind. He holds a PhD in cognitive neuroscience from University College London, UCL, and his recent publications have focused on AI for human cooperation and particularly human-centered mechanism design. And so I'm really glad that Raphael is here to join us as the second ever panelist in the series. When I started my PhD, I was kind of reading lots of Raphael's papers and kind of getting very inspired by them. So it's great to have him here to talk about them. Just in terms of the agenda for the talk, we'll go through now with around half an hour of talk from Raphael, with plenty of time for questions at the end. In order to ask questions, please use the Q&A function that Zoom offers. So if you haven't already found this, there should be the tab at the bottom. There's a little more option if it's not showing up for you already. And from there, you can hit the Q&A. So if you ask questions on there, you can also, I think, upvote and questions that you're most interested in hearing answered from other people. And then I'll pass those on for the second half of the call. So yeah, I think that's basically everything. There was a little bit there that flashed up before, I think, but yeah, this is kind of what we're aiming for with the seminar series. So yeah, big picture ideas, cutting edge results, and some critical discussion of things. If you would like to be kept informed about new seminars, including future seminars and future other events and so on, then just go to the mailing list. Okay, so that's all my housekeeping out of the way. So yeah, with great pleasure, over to you, Raphael, and thanks once again.
Thank you for having me, and thank you for this nice introduction. Just so that the audience knows, like I can't see any of you or like see the chat or anything. So I'm just going to go straight through, and then I'm really excited to answer your questions afterwards. And yeah, so as Louis said, I've been working on a bunch of topics that I think would qualify as cooperative AI. I want to sort of mention two that I'm not going to talk about. So one is multi-agent reinforcement learning, sort of to study social phenomena. That is really the idea that if you can observe something that would just happen in sort of blank slate DeepMind agents, it might be a really interesting model for that this could happen in animals or humans. And the much more novel one is sort of thinking of large language models as a tool for value pluralism, because they're very good at summarizing text. So they might be really good to scale a discussion, maybe a political debate, up to many participants and make sure that everyone's voice gets heard. What I want to talk about today is this column in the middle, which is more thinking from a game theory perspective. Can DeepRL agents help people to solve strategic conflict? And I should say in advance, this will not contain any LLMs at all. So if you're disappointed by that, I will not be offended if you log out. The rest of the introduction, I feel probably people in this audience don't really need to be sold on that. So social dilemmas hide in every multi-agent setting. And these tensions between individuals and the collective incentives are really difficult, no matter how smart you are. You cannot just solve them by becoming cognitively more capable. Like the game of chess is not going to have two winners just because both people are smart. And something like the prisoner's dilemma will always be a really difficult strategic conflict, no matter how smart the participants are. And mechanism design is a framework to design policies that can alleviate social dilemmas, taking into account that everybody acts strategically. So mechanisms are really common. It's like voting systems, but also just the fact that companies pay people to incentivize them to work at the company. Or if you write a paper together, you will have an author order that is trying to sort of give credit that is commensurate with the work that has been done. And if you stop doing that, it would get a lot harder to write papers because just the authors wouldn't be motivated in the same way. And how this is typically approached is like in economics, you may have a lot of strong assumptions. So The game is often assumed to be like tractable, so it's mathematically easy enough to do mathematical analysis on it. That's the beauty of matrix games. The human behavior is often assumed to be rational, optimal. Everybody's equally skilled or even perfectly skilled. So you might not even have to distinguish between people. You can just model one person. And then you don't even have to worry about inequality either, because there's really only one average person. That makes the human goal very easy, just maximize value. And the mechanism's goal is also very easy, which is to maximize the sum of value that's accomplished by the whole group of people. And this talk is about really that we can broaden these assumptions. So it's much more about the methodology, that if we use neural networks, we can like tackle each of these points. The first thing I want to talk about is the game. Again, if you're into like AI, you're probably easily sold on the idea that more complicated games that where neural networks can make progress offer you a lot more. So like these wonderful video games here at the bottom, or even games that incorporate natural language in some way, in contrast to like the simple matrix game where you just have two choices and it's really just like a one-off decision. What I want to talk about is sort of what I would call medium complexity games that you could think of as maybe similar to a board game. So they're still numeric, like only there's no language or pixels, but they could have continuous actions. They could have complicated, persistent game states. They could also have different roles for different players. Some players might have a different action space than another player. So then it would be too complicated for many traditional analyses, but neural networks could deal with this just fine. So that is sort of this middle ground that I'm going to talk about in this talk. And the goal is we want to build AIs that mediate social dilemmas. So think of a DeepMind agent. The issue with it is it's very data hungry, and typically you need a simulator of some sort to train it. And it's supposed to help real humans. These real humans are hard to model, they're not rational, and the data is very expensive. So how can you get these two together? Ideally, you would want to replace the humans with neural networks that act like humans, and then the whole training will get very easy. How to model humans? There are two large ideas. So one is that you think about the incentives. So you're trying to reconstruct the utility function of the human, and then that would be your model. Or what we're going to talk about is imitation-based, which is you just copy the human's behavior, and you just copy so much behavior that you're hoping you're covering almost all of it. And this copying has a downside. So for example, there could be equilibria that would be very hard to capture. Like let's say, if I only buy a phone because everyone else has a phone, or I only drive on the right if everyone else is driving on the right. If that's not in your data, it might be very difficult to get that out of just copying what people do and hoping you get a good model of human behavior. But you can see that we have already updated this table with our assumptions here on the right. So what I want to talk about is, rather than matrix games, these medium complexity games, and the human behavior and the human goals will just be copied from real humans. So we're pretty agnostic to how people behave. We just want to see real people's behavior. The mechanism goal we're going to keep the same for now, maximize the sum of value that is created for the humans. You may know this picture. This is a famous Behavioural agent from the DQN paper. So on the left, your inputs can be arbitrarily complex. In this case, it's pixels. The outputs are actions in the video game. And amazingly, all of these neural network weights were tuned in a service of maximizing the game score. Which seems like really hard to do. Like, how can you do so much with so little? Well, the answer is you get a lot of samples. And we want to use this in our training, but we're going to replace the input. It's not going to be video game pixels. It's going to be the contributions to a public fund in our little simulation of a social dilemma. The objective is the sum of player rewards, that's the game score, and the output actions are not these up, down, left, right, but they are the redistributions of the public pool. So that's the setup. And what's cool about Behavioural agents is they can discover novel strategies. So some of them on the right here are very famous examples of where an agent in the simulation discovers something that people didn't anticipate. but they need a really good simulator to do that. At the bottom here, you see a simulator from robotics and what's called sim to real. So if you have a simulator that is so good that you can train a DeepRL agent virtually and then it just works in the real world, that's really impressive. But then it's obvious the hard part is to get this really authentic simulator. So that's what we're trying to do. So first, we'll collect human data with different baseline mechanisms that are hard-coded. So one mechanism might just be distribute the pool randomly to everyone, or the equal baseline is just give equally to everyone. And we'll just gather a bunch of data with those baselines. And then we're going to train a neural network to just behave like those humans. So it will just conditioned on the previous step, what would you do on the next step? And that way you're basically encoding the whole data set, including the diversity, like including the different paths that people can take, you just into a recurrent neural network. Those are your behavioral clones, and then you train a mechanism in a simulation that is populated with these behavioral clones, and that way your DeepRL mechanism can train as long as it likes. And then you take your DeepRL mechanism and play now a new game with real people and see if this novel strategy that it has learned, if that actually works with real people. And if it does, then you've done a good job building a simulator. If it doesn't work, you can take all of this data and chuck it back into the behavioral cloning and make your clones better and try again. So the tricky thing here is during the training, the mechanism wants to explore new strategies. So that means it wants to do things that aren't present in the data. It kind of wants to take these behavioral clones off-piste. And in that situation, the simulation must be authentic to these novel situations that aren't present in the training data. If it works and the simulation makes a good enough guess of what humans would do in this novel situation, then you have a chance of like discovering novel strategies in the simulation that will actually work in the real world. So that is sort of the magic. That's where you're getting something novel out that wasn't initially in the data. So here's the concrete task that I want to talk about for this first part. We call it the trust factory because it's sort of an iterative trust game. It has a persistent pool. So you can imagine like these are supposed to be flowers. So you have like a pool of the resource that is persistent over 40 rounds. Every round, the mechanism starts with an offer. So it gives an offer to 4 players, and the players have to decide, what do I take home? That's the only way to get paid is to take this money. And how much do I give back? And the money that you give back gets multiplied by 1.4. This then continues for 40 rounds with the 4 players. What's interesting about this is that because it has this environment state, every episode could have a really different trajectory of like the pool going up and then the pool going down. So every game is really different. And the other thing that makes it really interesting from a shaping perspective is that selfless cooperation yields no reward, which also means that if the mechanism could sort of coerce everyone into cooperating, the mechanism would get no reward. Because the only way for the mechanism to get paid is for people to get paid, which is they need to withhold some money. So the key here is really to sustainably exploit the resource. So that's a much harder problem than just forcing everyone to cooperate in some way. And you can see different game trajectories here. This is under the equal baseline. In the top, we can see the pool size over the 40 steps. And you can see the pool size goes down. And when it's grayed out here for the 4 players, you can see their contributions, but also when the game is sort of over. This makes sense. Like the equal baseline promotes free riding. What the equal baseline does is the more you give back, the more other people get paid. So you will quickly figure that out and stop contributing. There is the proportional baseline, which has a different strategy. What it does is it gives a player on one turn proportional to how much that player gave back on the previous turn. So it's basically a tit for tat type strategy, and it works well in preserving the pool. But you can see here that player 4 was able to monopolize the whole game, and very quickly the other players were squeezed out, and only player 4 is playing with the mechanism. So what it does is it creates these inequalities by basically having these poverty traps and these feedback loops of that if you gave it too little once, it will basically freeze you out. The agent that we ended up training has a totally different strategy. You can see that it does a good job of maintaining the pool, but it also does a good job of keeping everyone in the game. And it even excludes people and then brings them back multiple times. So what it does is it seems to punish often, but also forgive very quickly. And that way it sort of keeps everyone in the game. Here you have our leaderboard. So here on the y-axis, you have the surplus. So this is the reward that the agent was actually trained to maximize. And on the x-axis, you have the Gini coefficient of how equally this reward was distributed across the 4 players. And you see on the left, you see the simulated games. On the right, you see the real games from humans. And the big dots are the center of mass. The small dots are individual games. And you can see that the mechanism that we trained gets a higher score on the y-axis. That is what it was trained for. But it also does a better job of distributing these rewards more equally compared to the proportional baseline. But this is basically just saying that the simulator works. If you can train a mechanism that beats all your baselines, then you've somehow been able to go beyond what you've programmed into the data set with the baselines. There's more to discover. This is too many plots to read, so just ignore what's on the axes. Just pay attention to the contours, which are simulated games, and the dots, which are real human games, and the colors. The gray means that the pool was depleted in this game, and colorful means that the pool was sustained that game. And you can see that pretty much in every plot, the dots and the contours match really beautifully. So the simulation is very accurate. If you look at the top right, you see the same plot that I showed you before with the surplus on the y-axis and the Gini coefficient on the x-axis. And you can see that under the proportional baseline, it's a very strong positive correlation. So what it means is if a lot of money is being made, that money is being made by one person. If you look at what our RL agent does here in the top right corner, actually the mass is in the top left. So that means the games that go well are the games that go well for everyone. That's mathematically not necessary in this game. Like the game doesn't care about whether all the contributions go and come from one person or whether it's distributed over 4 people. So there's something quirky in the way that humans play this game that's made itself into the behavioral clones and into the RL agent strategy that leads to this effect that the way to succeed here is to basically have everyone succeed together. And we can analyze the strategy of the agent more. So here what you see is, again, in the top row, simulations, and the bottom row, the real games. And what you see plotted is the Gini coefficient of the offer. So it means like, does the agent make the offer to all players or just to one player? If it's high, it means it's only going to one player. And this is then depending on how full is the pool currently. And what you can see is that the proportional baseline just pretty much plays with one player, irrespective of how full the pool is, because that's just its strategy. Whereas the RL agent, you see, it starts to give to everyone if the pool is close to full. So it's basically being generous and bringing everybody back if the pool is close to being maxed out anyway, because sort of like, what's the harm? Give people a second chance now that times are good. We've hard-coded this into a baseline that does exactly the strategy. And it performs really well. It performs as well as the agent and gets even like better scores on like that it's so interpretable and consistent. So you can try to reconstruct what this agent is doing. This is one of my favorite slides. So there's 2 slides that I have that I'm excited to show because something works a lot better than we anticipated. So this is a reviewer asked us to run the game 3 times in a row. So the agent was only trained to play one game. So like if people behave differently in game 2 or 3, the agent might fail because it doesn't really know how, it has never seen this behavior. And the reason I think why the reviewer asked this is because sort of economists never believe psychologists that humans act weird. Like if humans have a strange behavior, then economists pretty much go like, no, I just think you didn't explain it well enough. Like if people had enough training and if you explained it well, people would just behave perfectly rational and optimal. It's just that you framed it in a strange way. So I think this is trying to get at this. Like if people are really good at this task, would the agent still work? And it turns out you can see the proportional baseline the trajectory is actually worse. Like people get a worse reward in the third game than in the first, whereas under the agent, they just get better. So it's not just that the agent is able to adapt to this, it seems like the agent is really teaching people how to play this game better. So I thought that was a cool result because like I didn't expect that the agent would actually do better. Okay, so as I mentioned, this talk is really about like how we can remove assumptions and sort of use what neural networks can do to broaden how we use or how we think of mechanism design. And one of the last things we want to change is, what if we don't want to assume that the objective is the sum of player reward? Because as you've seen, there is like this trade-off between making a high surplus versus how is the surplus distributed across people. And it's not really clear how those two should trade off with one another, right? That's like a huge discussion people always have. So if we said like, what if we don't make this decision for people, but we let the players vote on what policy they prefer? And that's the signal that we're trying to maximize. So we're sort of even agnostic to what are you trying to accomplish in this game? How should the rewards be distributed? Take it from people, which we called democratic AI. It would have been much better for our careers if we had called it RLHF, but we didn't know that yet. So now we're going to update this table here and not assume the mechanism goal, but we're going to just follow human votes. But the game is going to be a bit easier. So the game now doesn't have a state. The game is basically just people play 10 rounds, but every round basically stands for itself and sort of resets. And there is the head player, which gets 10 coins to give. And then there are the 3 tail players who have as little as 2 coins to give. So there is a pre-programmed inequality. And every turn, now the players start. The players make a contribution to the public pool. The public pool grows by 60%, and then the pool is redistributed according to the mechanism policy. So the policy really is just mapping 8 numbers to 4 numbers. It is the 4 endowments, the 4 contributions, and then in the end, the output is 4 redistribution weights. So it's much simpler because you don't have to think about where am I in the episode, what happened before. It is just like one step. The benefit of this is that we can visualize the entire policy. On this plot here is what we call the libertarian baseline, which just gives back proportionally to how much people gave. And how you read this plot is on the y-axis is how much did the head player contribute, and on the x-axis is how much did the tail players contribute. So at the top right means everybody contributed on this turn. The bottom right, for example, means the tail players contributed everything, the head player contributed nothing and defected. And the color tells you how much does the mechanism now give back to the players. So it obviously makes sense. If it's proportional, it has these nice straight lines. It's dark blue if only the tail players contributed, so they get everything. If it's only the head player contributing, it's yellow, they get everything. It's somewhere in the middle if both contribute. So the libertarian baseline solves the social dilemma because everybody is incentivized to contribute. It maximizes the surplus, but it exactly preserves the initial inequality, which isn't very good for getting votes. We have a second baseline, which is called liberal egalitarian. And what it does is it basically shifts the whole color scheme to be more blue. So what that means is, given the same contributions, let's say everybody contributes here in the top right corner, the tail players will get relatively more, because what liberal egalitarian does, it gives back proportional, normalized by your endowment. So that means if somebody gives 10 out of 10, this mechanism thinks that that's as good as someone giving 2 out of 2. It's basically saying you gave everything you have, so we will consider that to be equally good no matter how much you had to give. This now naturally redistributes wealth because people who had less to give are on a level playing field in terms of how much they can give back, which is very good for getting votes. It does risk that the head player is defecting. If the inequality is too large, the head player might say, this isn't worth it for me. You're redistributing too much of my contribution. I'm not getting enough back. So let's see what our agent has learned. Our agent has learned this funky shape, despite the color scheme being almost the same as liberal egalitarian. So when everybody contributes, it does redistribute the wealth and redress the initial inequality, similar to liberal egalitarian. But what it has done is it has expanded the corners, basically the punishment zones, where people are treated as defectors. And it's basically saying here, if you are giving me less than half, I'm considering that as good as zero. And you really it's really not tolerating small contributions. So it sort of over proportionally punishes, which is maybe if you're playing with real humans, like more interpretable, it's like a clear threshold, and there might be advantages to doing that. So that is what the agent has learned, and that is how the agent actually overall wins almost every election. So we've seen two different games, like one stateful game where the inequality sort of emerges out of the player behavior, and one stateless game where the inequality is pre-programmed. And in both, the mechanisms, I think, have learned something pretty similar, which is to be generous when times are good and everyone's contributing and the pool is full. Then you sort of redistribute as much as you can, but you get very restrictive and punishing sort of when the situation is less good. And then you only interact with the people who are really reciprocating. But this talk is not about sort of the content of what the agents have learned, but it's more about the method. And you may have noticed that we've introduced one assumption as we've sort of stopped assuming that the game has to be sort of a neat, simple game. We don't make any assumptions about how people act. We don't actually make even assumptions about what the mechanism should accomplish. But we have introduced that you need access to reasonable solutions during training, but you also need a data set of sort of people playing with these baselines to sort of have a starting point of how you model humans. And my colleague Jan was like, what if we get rid of that? And we try to basically take an inspiration from AlphaGo Zero, and we actually start from scratch with a random neural network that just plays against itself. And I was like, that is crazy. That will never work. I'll show you why this wouldn't work. So how we get the votes is people play one episode with one agent, then one episode with another agent, and then they vote which one they like more. So what he suggested is, let's initialize a random agent, and people will play 2 games with an agent that has random weights. It's the same agent. You just play 2 episodes with the same agent, random weights. And then we get the votes. This is the policy of how the agent was initialized, and you can actually see it's the wrong way around. Like, it's brighter yellow in the bottom right corner and darker blue at the top left. So that means this agent happens to give you less if you give more, which is a terrible strategy. It's the opposite of what you should be doing. So we gathered around 100 games and just squeezed some information out of this almost worthless data, and created some behavioral clones, which are probably terrible, and then had the agent play itself in simulation, starting from random, just trying to win games against itself, in the simulation populated by these terrible behavioral clones. And as you can see, as you iterate, get a better agent, get more data with this agent, have it play again, make new behavioral clones, make the agent better again in simulation, deploy it again, gather more data. Very quickly, it learns that up is up and down is down, and that the yellow should be at the top left corner and the dark blue should be at the bottom right. And now it actually is pretty proportional after 2 iterations. And after 7 iterations, it converges to basically be the same model that we had before, where we just did one modeling step. So we took like the data of 4,000 people, put it into behavioral clones, trained one agent. If you do it like this, you can get away with a lot less data. What you're sacrificing is, though, you have to basically peek at the real world multiple times, which is a more sophisticated way of thinking about the modeling, because you're basically saying, rather than building one model of the humans that should always be valid, we know the model of the humans is only really pertaining to this one world we put them in, which is the one mechanism. And as we change the mechanism, we expect the humans to change. So ideally, we would want to update the humans, then update the model, update the humans, update the model. And if you do that, you are a lot more efficient. Of course, that might not be necessarily a safe thing to do. Like, it's fine for these kind of academic projects, but if you had a real problem in the real world, it might not be safe to start collecting data with a random agent and slowly get better. So you might have to always start collecting data sort of from a reasonable point. And I'm sure that could be done. I'm sure you could also just start it, uh, not have the baseline that you start training from be random, but something sort of somewhat reasonable, and then just improve it from there. Um, but yeah, so that's the other result that worked much better than we expected. The fact that it can sort of very quickly uh, squeeze something about this almost worthless data and uh, start to do something reasonable, that really surprised us. So that was pretty cool. Thank you. That is all I have.
Okay, nice. Thank you, Raphael. I'm sure there's rapturous applause going on in like across in front of laptops across the world, but unfortunately you can't hear any of it because yeah, of the participant thing. But yeah, that's fantastic. So I have now there's already a bunch of questions that people have been asking. Just as a reminder to everyone else now in the audience, if you haven't already found the Q&A kind of button, now is a great time to go and find it. You can both ask your own questions and upvote questions that are already there. I'll basically just proceed by kind of like asking the most upvoted questions and we'll kind of work our way down the list. So yeah, do add things there. Right, so the first one that I will, okay, a new one has just risen to the top, so I'm going to ask that one first now. And this is maybe touching on one of the things that you mentioned right at the end, which is, this challenge of if you were implementing this in the real world, then you might not want to have this kind of like, fully interactive, iterative kind of process, and you maybe want to kind of initialize it from some sensible baseline. So the question kind of is somewhat related to that, which is what real world application domains or kinds of real world application domains do you think are most appropriate and or most exciting when it comes to these ideas?
Yeah, this is something that we struggled with a lot. Like we couldn't really quite find uh, a real world application that made so much sense to us that we were like, oh, we actually want to do this. It's kind of, or not, it didn't rise past the threshold of us actually getting involved with it. My favorite example, which comes very close, is I believe there is a YouTube video that is, I think, only dedicated to it's making very long videos about Disneyland, the history of Disneyland. And one video is called The History of FastPass. FastPass is Disneyland's mechanism on which ride you can take when. And it takes you through the whole history of, I think, like in the 50s, it was basically you just stand in line and then you go. And then they were like, well, we create basically these passes that sort of allocate you to specific rides at specific places, which created certain incentives for the people who go and also for the park, because they have other incentives from the people. They want everyone to go on a lot of rides, but they also want to spread around where they currently are and make sure they go to restaurants. And then people started to exploit that system, and they had to patch that system. And it was this like decade long back and forth of how do we allocate people to the different rides, and what should we even maximize for? Should people just be happy at the end of the day, or should they maximize for the number of rides taken? And also inequality that turns out, and the second half of the videos, I think he does an agent-based simulation on different mechanisms on how to sort of distribute people onto the rides, and the inequality that comes up. And I think is also currently the case that if you know a lot, then you will take many, many rides. Whereas like if you're sort of, you don't prepare yourself, you'll go on very few rides. So I thought that was like that was like maybe the closest example where I was like, yeah, this is also that they have data on all of this. It's like this is maybe the closest that I can think of where if I had to sell someone on this framework to do their job differently, maybe the people who are in charge of Disneyland FastPass. There is, of course, the paper, The AI Economist, is, of course, sort of the attempt to think about it's not as much grounded in human data, but they are trying to think of basically, could you design a tax code through a multi-agent simulation? And it's obviously also kind of a toy example, but you could imagine if you took this very seriously and you made a very large, authentic simulation of an economy, then maybe you could come up with examples like this. I think there are also some economists who use agent-based modeling who are involved in policymaking, but I think they are not as close to actually making decisions based on this as like sort of the more traditional approaches.
Nice. Yeah, I actually, that was going to be one of my, I guess, separate questions, which is I think a lot of the things in here that kind of, yeah, it did make me think a little bit of the kind of AI economist and so on. But that in turn, when it comes to this question of application domains, for me at least, it feels much easier to think of application domains at the kind of like societal level or something, or alternatively at the very kind of toy small level, and actually trying to find these ones in the middle is seems quite challenging. So, but the point about Disneyland is a good one. Yeah, someone's requested the video in the chat, so we'll try and find that and hunt that down for you and pass it on afterwards. Um, Cool. Okay, and I'll move to the next question, which comes from Martin. So thank you for the talk. After the execution of the human behavior copying workflow to build the RL agents, are any systematic effects visible where preference or behavior impurities kind of remain and therefore impact agent behavior from the underlying and inherent AI agent preferences and utilities during pre-training of the agent base model? And then the follow-on question is a baseline evaluated from agent performance without applying the human behavior copying workflow, and then results from the agents after human behavior copying corrected for this baseline?
So I'm not sure if I got this. So I think one thing is like you can basically look at the veracity of your behavioral clones pretty much like in the same train test way how you evaluate other models too. The issue, of course, with that you expose them then that really you don't care that much about how good are the behavioral clones. You care about like does the mechanism agent, does that one get weird if the behavioral clones get weird? So if the behavioral clones were very brittle or very exploitable, you would see game trajectories, but also like behavior that's just very, very strange. So that hasn't really happened. Like at least we haven't really seen it, maybe because we were obviously careful not to overfit them, but also as long as your game, which is why we use these toy domains, like as long as that is more or less inspectable, like this is why in the first study we had like you could just visualize the policy, so you can sort of tell if something very, very strange is going on. But it has never really happened that it like completely broke. I think one, I'm not sure if that was the question, but there's also like there's a whole question like, do you actually need the human data at all, or could you just have RL agents play with RL agents? Which we explored in a different paper that I didn't present. So there, I think the answer was it may work if you don't take the voting into account. Like if you just care in the second study, if you only care about maximizing the surplus, then that approach can work. I think there the expensive part was that essentially you train your players, the deep RL agents that are the players, you train them to convergence, and then you only basically do one training step or very little training on the mechanism. And then as the mechanism has changed a bit, you now let the players learn again. And that way you basically have this loop that is just kind of expensive to run, where basically you should be able to become also not exploitable, because every single time the players would learn to try to exploit the mechanism and reach some sort of good strategy, and then you update your mechanism again. So if you think that humans don't act quirky and there's actually nothing to gain from grounding it in human behavior, and you're actually happy with the assumption that like the deep RL agent just maximizing reward should capture most of what I think people are doing in this task, then that should totally work. Then you don't have to mess around with like getting human data at all.
Okay, interesting. And so when you say it kind of the divergence came about when there was the introduction of this kind of voting mechanism, do you think that's because humans have particular kind of biases or ways they kind of approach voting questions or task, or kind of apportioning credit in certain ways that kind of would differ from a kind of like purely kind of utility maximizing RL style agent? Or do you have any idea why it was that well, maybe it was just added
Yeah, I'm trying to. I mean, we didn't
um,
investigate this as thoroughly as these were sort of like two little like follow-up investigations. So I'm not really sure uh, what the exact part was that was missing. I think you could imagine that for the voting, there is maybe a certain amount of, I mean, this is a subject of sort of classic, like let's say, is it the ultimatum game? Yeah, where basically people
mm,
reject offers out of spite, which is very similar that just in these types of games, your exact point of where you start to defect or where you get frustrated um, might not be exactly the optimal one. That's one point. And the other thing is that this could go two ways. You might have some people who are a little bit more generous or just slow to defect, and some people who are much faster to defect or who are more spiteful and get more frustrated more easily. And because you're modeling the whole trajectory of someone, if you're sort of always conditioning on the previous turn, you should be able to capture some of the individual variation in this personality in someone's trajectory. Um, so while the game might be stateless, the behavioral clone isn't. Like the behavioral clone just goes
mm,
like it has the
yep.
whole history of all previous steps. So that should give you certainly a better fit in both of these directions on not just if people on average deviate, but if individual people could deviate in both ways. Um, so that's at least like this personal threshold. People definitely differ a lot in like how spiteful they are, or when they stop collaborating.
Nice. Yeah, that makes sense. Thanks. Great answer. Cool. Next question, which I suppose you kind of, maybe unintentionally set yourself up for in the kind of like early moments of the presentation is the following, which is, so you mentioned the work you discussed in this talk didn't make use of LLMs. What do you think would be the biggest challenges in bridging that gap?
Yeah. So the project. Let me go back to the first slide.
Hmm.
Um, there is a paper that is called "AI Can Help Humans Find Common Ground in Democratic Deliberation."
Yeah.
That was sort of the that came from the same idea. Like if our blueprint was we want to have a group of people and we want an AI to help people to overcome this. Um, what is the natural language equivalent of that? If you're thinking like this is the game theory version, like you come up with some sort of social dilemma that is like a numeric one, and you sort of just by setting incentives, like just by how you distribute the money. So this is like very much purely in like behavioral economics world. The question was like, if we use LLMs for this, well, one thing is you could have said, can we have LLMs just talk to people so that they will consult people to talk themselves out of the social dilemma or just explain the game well? Could you just, if you are stuck in a strategic conflict with other people, could an LLM advisor fix it? But then we thought like, okay, maybe that's not thinking far enough. What if we also just change the problem to be sort of the natural language equivalent problem, which seemed to be, democratic deliberation or just sort of any consensus finding on. I mean, obviously, if you're involved in any organization, like how do you make decisions as a group? Like that's a hard thing to do. You typically do it in natural language with like Slack and email chains and like meetings. Um, but then also on a societal level, that we just felt like uh, polarization is a really big issue, and it might just have something to do with the flow of information. Like, uh, do you have enough exposure to sort of opinions that could inform you or also like moderate your opinion if you just are exposed to a lot more? And that sort of led to this. So I felt like rather than trying to bridge it, we just felt like let's just go all the way and try to come up with like what would be the LLMified version of this research program.
Nice. Yeah, that makes sense. And I'm also actually, yeah, big fan of that paper. I recommend anyone who's in the audience who hasn't actually read that yet to go and have a look. Yeah, I think that definitely makes sense as one kind of avenue that one could go down. I think also maybe relevant to your work. I'm not sure what you think of this, but there's been a lot of kind of excitement about the possibility of using LLMs as kind of human proxies in some of these more kind of social science experiments and so on. And that seemed to be one kind of core element of your work that was maybe missing from some other people who've done this kind of similar idea of like, the AI economist or kind of those sorts of things. And so to the extent that maybe LLMs can serve as even better proxies in more complex environments, I wonder if that's something that is like potentially kind of something useful.
We haven't tried that. I think that would be a really sobering baseline if we would just plug LLMs into our exact um, experiment and just say, this is the situation that you're in. What would you output as a number? And if it can like do a good job of approximating what humans, or like as good as a job as the behavioral clones, then yeah, then the LLMs are a very good model out of the box. Like I'm not really sure. Like I keep going back and forth on like there's a lot of papers which are very positive about this, that they're basically saying, look, across many sort of well-established tasks, the LLM can more or less make reasonable guesses around like how people would act.
Mm.
And then I don't know, then other papers are more skeptical. I know people who look into it themselves, and it's sort of a mixed bag of like it varies model to model. It varies a lot on the framing. Um, yeah, it's kind of, I think in principle it will be possible. It also, I think it depends a lot on the domain of like what are things and framings that the model knows a lot about. So if you just make it seem a lot more alien, like um, it might stop doing good predictions. So yeah, I'm neither I'm not like one of those super skeptics about it who's like LLMs shouldn't be able to do this and they can, but I'm also uh yeah, it's just kind of, I think right now it's a bit of a mixed bag.
Yeah, no, that sounds right. This is also my impression, although it's not something I've followed quite as closely. But yeah, cool. Thanks. Okay, so we have some more questions still remaining. If it's okay, keep firing them out. Someone anonymous here asks that they didn't understand how you solved the weakness of the behavioral cloning models in the sense that they can't predict unobserved equilibrium behavior. Did you mention that you gathered new authentic human data when your simulator encountered out of distribution states while learning a better policy? And relatedly, do you think what are the pros and cons of using behavioral cloning or preference modeling? So a bunch of
So
questions
it
there.
turns out, so the unobserved equilibria, I think basically just wasn't an issue. Like it didn't come up in our specific uh, games. You could argue, let's see. So in the first study, there's basically you gather your data, you train your behavioral clones, you evaluate your behavioral clones with a mechanism and see if it goes well. If it doesn't go well, you can use this data and basically chuck it into your data set that you use to train the behavioral clones to begin with. So that we have done in the first study. So you could kind of argue, rather than the behavioral clones being able to handle the behavior of the um, of the final agent, it was only able to like get an agent somewhere in the middle, and like, so because basically also all the baselines are linear, right? So it will just, you will have one neural network that then introduces sort of much more quirky nonlinear behavior, and maybe you need to put that into your behavioral clone first, and then it has learned enough about this that it can extrapolate a step further. So you might not be able to take the whole step at once, which is basically the same as what I've been showing here, that like um you, rather than saying, okay, we only did one step, you could basically say like we started somewhere reasonable by having a big data set that already covers a lot of interesting things, And then we peaked at the real world once, got like with an agent that was as good as it gets, and then we make a better agent that in sort of 2 iterations. So that's sort of the hybrid approach here. But I don't think it gets around the overall issue that like really big changes would remain completely unobserved. Like you need to
Mm.
somehow maybe find a way to hint at them in your data set. And yeah, and we've never really we've never explored the incentive-based models. Like because the behavioral cloning worked sort of at first we tried to do it without behavioral cloning by just sort of hard coding bots where we were like, if we can just hard code many different strategies or also
Mm.
parameterize many different strategies, we can just come up with like similar, I think, how most cognitive modelers think about this. Like, can I just describe the human behavior in maybe 5 different factors? And then I just create a huge population that have different values for these factors. And then like I create so many diverse games, we never need human data. That was the first approach. And it didn't really work. Like we didn't
Mm.
manage to create really good bots. And then we just tried the behavioral cloning and it worked really well instantly. And we never tried something else. I wonder if maybe other ways of creating, as long as it's sort of creating neural networks from human data, I imagine those approaches would be just as good. Like in the end, you can just sort of tell, like, do you have a good fit to the data and is it not massively overfit so it can still like explore a bit in the simulation. I mean, you could argue that your ability to extrapolate to novel mechanism behavior would be higher if you had sort of incentive based models, but like we've never tried it. I'd be curious if somebody ever looks into like a direct comparison of the two.
Okay, nice. Challenge to someone in the audience, perhaps, who wants to take up that mantle. Okay, I think we've just got time for maybe one or two quick questions towards the end now. So the one currently at the top is from Propel, which is, I'm wondering what the relationship is between the learning capacity of the RL agent, by which I think in this case is the kind of the mechanism designer type agent, and the learning capacity, which in this case Propel is kind of equated with kind of the depth of the parameter count, etc., of the neural network representing the humans. So in other words, if the kind of human neural network is deep enough, can these more intelligent agents force the RL agent to fail in creating cooperative mechanisms? Can they overexploit maybe the mechanism designer agent?
So I'm embarrassed to say that I think the network size is not an issue at all for games that are so simple. Like I think if you did this with very small, I forgot exactly what parameters we were using in the paper. I think like always medium sized sort of LSTMs, but I'm actually when I played around with it a bit, I felt like even very small networks do a pretty good job. Like, especially for the second study, where it's really just like mapping 8 numbers to 4 numbers. You don't need like an enormous LSTM to do it. Like a very, very small one um, does the same job. So I think in this domain, at least in these really small toy games, I don't think there was a lot of opportunity for sort of outthinking or out exploiting your one side or the other. Um, yeah, but I think this would be really interesting in sort of more complex situations.
Okay, great. Thanks. I think, yeah, let's see how we go. This might be our last question. So the one here is, and actually very closely related to the thing you just mentioned, which is you highlighted the importance at the beginning of the talk of moving from these simple matrix games to what you described as these kind of like moderately complex games, like definitely like a bit more complicated than the basic ones. Um, do you expect those latter kind of slightly more moderately complex games to be sufficient to be good at understanding kind of real world complexity in certain cases at least? And if not, do you think that the step between those moderately complex games and kind of real world complexity, even if in limited domains, is going to be easier or harder than the step that bridges from like very, very small kind of matrix games to like the slightly more complex and interesting kind of moderate games?
I so I can just tell you what I would have liked to have done if let's
That's
say this
perfect.
research program
Yeah.
had continued without LLMs having happened.
Right.
I think the natural next step would have been to think about papers like the AI Economist, or there was a DeepMind paper that was also sort of looking at these types of 2D environments, but sort of how basics of an economy just emerged from agent behavior, like that agents learn to do arbitrage or they learn how to trade.
Mhm.
And if both of if you could have combined that in the next step to think, okay, can we take it might still be a 2D game, but in a 2D game, can we have lots of interesting economic interactions? Like it's like a little economy, lots of incentives, lots of competition, and ground that in human data, compare it to what happens if just RL agents play it. Maybe then it's too complicated and or the human quirks are really important. So let's do it with behavioral clones, and then sort of do mechanism design in this sort of video game environment. That I think would have been the next step. And then I was really excited for, well, let's say during COVID, people made decisions based on computational models that were real
Mm.
policy decisions. Like, um, and sometimes these models were extremely simple. Uh, it would be, this is a kind of a really utopian view far out. But if you could imagine, what if you had like a whole city simulated, fully populated with agents that have a whole day where they really walk, like it's an entire uh, really like to every motion, like that they, and then you would have things like, I don't know, people sneezing in elevators and then the aerosol staying in the elevators, and then you say, oh, what if we all wear masks? And then some agents discover, well, when I wear the mask, my iPhone doesn't unlock because I just got the one that has the facial recognition. And you would get all of these little things that you wouldn't be able to pre-program into your model, where you sort of, if you're writing it down by hand, you wouldn't get all of these small interactions that you get from rich simulators. Like that's sort of the cool thing about um, these video games, is that you just get a lot of the really interesting behavior for free because they arise from interactions with this environment that the programmer didn't anticipate. Um, and that uh, would be like the incredibly ambitious vision of, if you put all of this together, like you put the sort of multi-agent RL stuff in really complicated games together, you try to scale that up to massive 3D simulations, and then you ground it in human data, and then you think about policy interventions. That would sort of be the absolute maximalist dream of where this could go.
Nice. Okay. I mean, a utopian vision and a maximalist dream, I think, is a fantastic place to end on. And we've just about run out of time as well. So thank you once again, Raphael, for presenting the work and kind of being so kind of, yeah, patient and forthcoming and answering all of those questions. Thanks to everyone in the audience for asking the questions and for joining us. And yeah, stay tuned. There'll be another seminar happening in around a month from now. We'll be emailing about it soon. And yeah, so until then, thanks very much.
Thanks for having me.